Okay, it is 11, 10, 16. And up to now we've been talking about the whole darned electron. We've been talking about the overall structure of electrons. We've been talking about their nucleus versus where the electrons live. We've been talking about how we found all that stuff out. So now we're going to very specifically start to talk about the electrons in those atoms. Because what you may or may not realize is that everything around you, everything you've ever touched or interacted with, is dependent on how its electrons are arranged. The way that all matter behaves is really largely down to how its electrons are arranged. And you kind of get that in physical science, but we're gonna do a lot more with it here, as you would expect. So first, we want to sort of recap and refresh what we know about the atom. And what we know is that we work with, in this level of dealing with atoms, we work with the quantum model, and that comes out of Planck's work very early in the 20th century, late 19th, early 20th century. Einstein and de Broglie contributed pieces pairing onto what Planck had already said. And then Heisenberg and Schrödinger kind of come in and frost the cake, so to speak. They lend us our final bits of understanding about how electrons are arranged in atoms. So the model, in completely lay terms and continuing with our theme of things we can eat, is a big giant ball of cotton candy. And if you want to really continue with the thing of things you can eat, you can imagine that there is some sort of jawbreaker in the center of that. So cotton candy to fill up, I don't know, this room with a teeny little jawbreaker in the middle of it. That tiny, very hard, very dense, it's not really hard, but that dense positive center. And we've got this image that often gets used, but it's a pretty good one. The thing that we actually know from Schrödinger is that ball of cotton candy is not just one ball of cotton candy. Some year I should get cotton candy and we should actually build. I hate cotton candy. It's disgusting and it's sticky and it's messy and it's gross. I don't even like the smell of it. But it would be a great thing for this. Maybe we can find an old cotton candy machine and bring it into the chem lab and completely coat everything with powdered sugar. So it's not one continuous glob of cotton candy. There are little sub-globs of cotton candy in that giant, fuzzy, sticky ball. So here's that word orbitals. And this comes out of Schrödinger's work. And we referenced this when we were talking about the history of the atom, but I'll repeat it because it's worth repeating. You have all written equations for lines. I can give you y equals mx plus b, and you can plot a line on a graph on 2 dimensions on an x and a y axis and understand that mathematical equation represents a line within a coordinate system. What Schrödinger's equations are is 3-dimensional equations. So you can have a 1-dimensional equation, which would be, like x equals 2. Gets you a 1-dimensional equation. If you want motion on 2 dimensions, you have to add a y component. Schrödinger's equations have an x, y, and a z component. Don't even think about trying this math at home. It's ugly, it's hideous, and it'll make your head hurt and possibly make your eyes bleed. But these 3-dimensional regions that are described by Schrödinger's equations are orbitals. And the orbitals are a 3-dimensional region around the nucleus where there is a high probability of finding an electron. Why do we say there's a high probability and not that that's where it is? Whose work tells us we can't pin them down? My hero, don't forget him, my darling Werner Heisenberg. Heisenberg's uncertainty principle. So Heisenberg said we can't specifically locate an electron. We can't measure both its velocity and location at the same time. But with Schrödinger's equations, basically what we get is a high probability area. So it's an area where these electrons tend to reside. And we can't pin them down exactly, but we can narrow the field a bit. So these orbitals and groups of orbitals have different amounts of energy. So this is pretty much the last time you're ever going to hear about most of these quantum numbers. I'll read it, then I'll shut up and let you copy, and then we'll discuss a little bit. In order to identify electrons and get as close basically as we possibly can to where that electron lives, we kind of have to assign an address to it. And I think that's the easiest way to understand the quantum numbers. So we use quantum numbers to sort of locate these positions. And the principal quantum number is the only one that I'm going to ever really expect that you know the name of. Principal quantum number is also identified as n. We'll say n equals 1, n equals 2, n equals 3. And it's the main energy level. So it's the first, second, third, fourth main energy level. The angular momentum quantum number is identified by L, but we don't care about that. And really, we don't care that we call it the angular momentum quantum number. What I care about is that you understand is that that second level of sort of addressing, clarifying, and identifying is all about the shape of the orbital. That's what I care that you know. The magnetic quantum number identified as M, once again, I don't care that you know it's M. I don't care that you know it's the magnetic quantum number. What I care that you know is that that third level of identification is about how it's arranged around the nucleus. Okay? So the first level of identification is just what main energy level it's on. The second is what shape the orbital is, and the third is how that particular shaped orbital sits around, if we think of it as a three-dimensional Cartesian coordinate system, how it sits around the origin. That's what matters. And then spin quantum number, we kind of care not so much about the fact that it's a quantum number, but we care that this is called spin. And this is like the final address line on something. I don't care that you know that the values are plus 1/2, minus 1/2. We usually say up and down anyway. And what this does is it pins down which electron we're talking about. Now these addresses are not permanent. It's kind of complicated, but what you need to know is that that fourth level of clarification that identifies an electron is its spin. So really there are a few things you need to know on here. If you go into your textbook, you'll find a much more in-depth explanation of the quantum numbers, but I think that at this level of chemistry, it's not necessary, and I think it's just more work. I'd rather get you to the stuff that is really important, so let's do that. This is this crazy little graph that I made years and years and years ago because I really struggled with how to teach this, and this is the only thing that I have found that works. So it continues to evolve, but you'll notice that along the side I say energy is going up as we go up. Okay? So on the bottom, the first main energy level we're going to talk about is the lowest main energy level that exists, and that's energy level 1. Main energy level 1. So n equals 1, and we can actually put in there n equals 1, n equals 1. So we're talking about the first main energy level here. And you can think about this, I very often use the metaphor of a high-rise building, and we'll get up to the 5th floor probably tomorrow, well not tomorrow, probably Monday. And on the first floor, if you jumped out the first floor window, would you have a lot of gravitational potential energy? No. You'd have almost none. You might sprain your ankle. So the first floor is very low energy. And in this particular high-rise building, if we're going to continue that analogy, the first floor also has only one apartment. There's only one shape of apartment, only one style of apartment, and there's only one shape of orbital here. And that's what's called an s orbital, and it's called an s because it is spherical. It's an s orbital. Okay? And when I say spherical, this thing looks like a beach ball. It's small, it's spherical, it's an s orbital. Woohoo! Now this obviously is an s orbital that's standing on a little sort of stand to elevate it. That's not part of the orbital. Just the little pink sphere is the orbital. And the rest of it's just the stand that's holding it up. If you tried really hard, could you arrange a beach ball in some way that it would look different from the front? Think you could do that? Think you could turn a beach ball around the origin so that it looked like it wasn't a sphere anymore? No. There's only one way to arrange a spherical object, because it doesn't matter how you turn it, it looks the same. So for s orbitals, guess how many directions there are? 1. So we only have one s orbital. So on this entire first main energy level, there is a lonely beach ball. That's it. There's a single orbital there. Now we're going to get into how many orbitals an electron can hold, but how many electrons an orbital can hold. I think I reversed that. But what I'm going to tell you is that for every electron, it's going to get an assigned sort of address or spin of either up or down. And it's hard to see with the little doceri highlight there, isn't it? Up or down. And we usually do those single-headed arrows. Okay. Well, after we finished up with the first floor, guess where we're going? Second floor. So n equals 2 is the second main energy level. And on the second main energy level, we actually have 2 shapes. Okay? So every energy level gets a beach ball. Every energy level gets an s orbital. There's our s orbital. I'll even label it. It's a spherical orbital. And the second orbital shape that we get on the second main energy level is this thing. You can call it a double drumstick. You can call it an infinity sign. You can call it a barbell. You can call it whatever you want. But that's what it looks like. Some people think it looks like 2 chicken legs shoved together at the knee. I don't know what you want to call it. Hence the double drumstick. But that's called a p orbital. Okay? That shape is referenced as a p orbital. Now, I have a p orbital here. And it's 3 ways. Now here's the rule. If it's a way that you can orient an orbital, there's a separate orbital oriented in that direction. So, guess how many p orbitals there are? 3. 3. They exist, so we have the one little boring s. We have one p orbital that's oriented on the x-axis. We have one p orbital oriented on the y-axis. And this one's kind of funky to draw. One p orbital oriented on the z-axis. So we have a total of 4 orbitals here. Because we have one s, we have 3 p's. And within each of those orbitals, every electron is spin up or spin down. Now, we're going to stop there, but I'd like to invite you to do a little dance with me. So we'll pause this. You can stand up. Never mind, we'll do it on our way out.